Now that we know how to drive our LCD and touch panels, it's time to make a game. So let's code Breakout. Hi and welcome to Bytes and Bits. If you've watched the previous videos in this little series, you'll know that we've been working with one of these little LCD touchscreens. And we've been seeing how we can both set it up, program it, create animations, and then calibrate it. So let's bring all of that together today by actually writing a little game. So as you saw from the intro sequence, we're going to be looking at Breakout or Arkanoid, which is a little game where we have a bat down the bottom, a ball bouncing around. When it hits these bricks, it destroys those bricks, and that basically is the game. So we're going to be using the LCD screen as our display for this game. We're going to be using the touch screen input to control the bat, and we're going to put it all together using our Arduino. So let's get straight into the code and work out how we do it. So I've got here the Breakout code. Now all the code in this lesson is available on my website, so please check on the description on YouTube and you'll see a link down there to the project page for this. And again, you'll get links as well from there to the various other videos in this series, or indeed I'll put a little link up in the top corner to the playlist for this particular video series. But as I say, all this code is available for you just to download and bring into your Arduino or IDE, and you can then test this out for yourself. So the actual code itself then, I'm going to take you through it bit by bit. And really what we're going to do is I'm going to disable certain sections of the code so we can see each bit as we need to put it together, and then finally build up the full game. So the first sections of code we're going to look at is the real setup of the game and then producing the various game states. So the start game, the play game, and the end game states. So the first bit we do is to, once we first turn on the TFT screen, we need to calibrate the touch screen with that. And again, if you look in one of the previous videos, you'll see that whole process taking place. So really that's the very first thing that we're going to do. So we're going to come in, we're going to set up the TFT, we're going to set up the touch screen. There's a number of variables we're going to be using throughout our code, and a block of those are to do with the calibration of that screen. So we're really there matching up the values we get back from our touch panel with the pixel values for the left and right and up and down coordinates. So that is handled. So if I come down here a bit more, we have a function called calibrate touchscreen, and that really then it puts a couple of crosses on the screen. You have to touch those. It then reads the values off the touch screen for these known screen coordinates and then calibrates the various values that we're getting back so that we can then translate coordinates coming back from our touch panel and then translate those into actual screen pixel coordinates. And at the end of that, we end up producing a model for our touch screen, which is based upon, in effect, two straight line translations for our x coordinates and our y coordinates. So you can see here that we are modeling our x coordinate translation function as a straight line, and then our y coordinate translation function as well. So if we actually have a look at the setup code, so again, this is the first bit of function that the system will run. So we are doing so from here down to here is our normal initialization of our LCD screen and our touch panel. So you can see that we are writing to the various control select or chip select signals just to make sure that we don't have any select contention at the beginning of it. We're then setting up our screen, so we're setting its rotation so that we actually have it as a landscape screen, and then we're filling it in black. We're making a note of the size of the screen, and we're then starting off our touch screen. And there you can see at the end of this setup function, we're calling this calibrate touchscreen function, which will go through the whole calibration process and generate that model. If we come down to our main game loop, which is just down here, I can find that for us. Okay, so here's our main loop. So again, we are going to limit the frame rate to 50 frames per second. And again, if you look in the previous videos, you'll find out how we did that. So basically, we are logging. This function millis tells us how many milliseconds it has been since the Arduino booted up. So we take a note of when the last frame ran, we have a look at what the time is now, and we don't let this frame run until at least 20 milliseconds have passed. So that will give us a maximum frame rate of 50 frames per second. If our code is running a bit slower than that, then yes, we will get a lower frame rate, but at least it means that we have some way of controlling, making sure that the speed of the ball doesn't vary too much as we work around. So that's what that first little bit here is doing. And now we have our state machine then. So we're storing the game state in this variable. So this is a global variable game state. So state 1 is where we're starting the game. So actual state 1 then just simply filters through into state 11, which is where we draw a little button on the screen. So that's just drawing a button on the screen using rectangles and text. And then it's setting it up to state number 12, and state number 12 is where we wait for that button to be pressed. So we put a button on screen saying click to play, and then we loop around in here checking if the touch screen has been touched. If it has been touched, we work out if that touch point is inside our button, and if it is inside our button, then we initialize our game. And we then go on to game state 2. Now at the moment I have blocked out the initialize game function, so that will just simply come into the play state. It will wait for 1 second and then go to the end game state. So this is really just to try and make sure that we get the overall control flow of our code working. So we should be able to turn the board on, check our calibration, put up a button, click the button to start the game will automatically finish, and will then finish back out down here in our end game screen state, where we again clear the screen and we print up our score and put up a new button which basically says to play again. And at that point it will go back to our game start state. So that's really just a bit of what we call sort of boilerplate, which is really just what every game needs is a little state machine that helps control the game start. When the game finishes, then it handles the game finishing, so we can then play a second game after that. So let's upload that into our Arduino and see what happens. So that's compiling and uploading up to our Arduino. And once that's up and running, we should be able to see our screen go into calibration mode. So there we go, and there's a little first red cross appearing. So we click on that. We then have our second one appear, we click on that, and that's the screen calibrated. So it's now in the game start state, so it's waiting for us to click this button. Once we click that, our game would now go into its play mode. And then of course at the moment we've just simply got it sitting in the play mode for a short time and then coming out to the end game state, where again we've got our button to play the second game. And there we go, and then back to our end game state. So that's the main control layer of the game written. So most of the basic sort of functionality to get the game up and running and then get us to the various game states. So let's start looking through the actual code to play the game itself. What I'm going to do, I'm going to bring each block of the game code in bit by bit, so we can see how it's all built together, and you'll see how I've programmed it. Now I've actually programmed it using a mixture of procedural coding, where we're going to use various functions to implement our blocks of code, and then the actual game blocks, the actual sort of bricks in the game, are implemented using object-oriented coding. So you'll see the difference between the two. And again, it's up to you what methodology you use. I tend to go more towards the object-oriented whenever I program, but as you see here, it can all be done using procedural-based as well. But anyway, that's something for you to have a think about as you go through. So let's start looking at this code. So we know that after we've done our setup and so on, we come down into our loop function. And again, that is part of the sort of standard setup for an Arduino sketch. And the loop function then is designed to be called continually so that our code can run. And then when the loop finishes, the Arduino sometimes has to do some of its own housekeeping functionality, especially if you're using some things like serial channels and various other packages, that they may need to have some compute time, which tends to be either side of the actual loop running. So your code, you don't really want to get it caught up inside this bit of code and trapped there. So you really want to sort of make sure that you let the loop finish and then come back around and then redo your next bit of code on the next loop update. Again, that's not a hard and fast rule, and if you know what you're doing, then obviously you might not need to let the loop escape back out and do something. But anyway, in this sort of game programming, I'm using that, again, partly to control our frame rate here. So we need to let the loop function complete so that we can come back around and then limit our frame rate. But also then, when we use our state machine, it makes that a much better way of implementing our game. Okay, so this switch statement, as I said, that creates a state machine. And the basic idea here is that when we come through, our loop function runs, the state machine is really executing a block of code, trying to work out whether we need to move to a different state, and then letting the loop finish. So you can see here we come in at game state 1, and that simply then switches to game state 11. State 11 draws a button on the screen and moves to state 12. And at that point, our state 12 is an area where we could lock the code here and have it continually looking to see if there's a button press. But using the state machine, what we can do is we can say, have we got a button press? If we haven't, we just let the loop continue, so we don't lock the code up in here. If we have got a button press, you can see that we will do that. We do various bits of code here, so we're going to be having a look at this init game function in a second. And then we move on to state number 2, which is the play game state. So we don't actually ever lock the loop up in this bit of code. But again, that's how I program these games and so on. And a lot of the software that I would write for Arduinos, I would write in the same way, using a sort of state machine type process, which lets you take advantage of this looping structure in the Arduino sketch. But again, that's entirely up to you. You don't have to do that. But let's start having a look at the actual then building up of the game. So we've said here that we do call this function initGame before we actually get into the play game state. So let's have a look and see what that does. So let's go up and see where that is. So if we come up here a bit and up to here, right? Okay. So our initGame function then. So when we call that, we will generally have been in a position where we've got a button on the screen. So we're going to clear the screen by filling it in black. We're then going to draw the various screen decorations. So at the moment, I have a little area at the top of the screen which holds the sort of level and score and so on. So we're going to draw that boilerplate text in. So you can see here it's drawing a line. It's then drawing the word score, the word lives, and the word level. And again, if you remember back to our previous tutorials on using our LCD screen, using this SPI interface, we really don't want to be redrawing bits that we don't need to redraw. So these screen decorations are actually fixed, so we only need to ever draw them at the start of the game, and after that we can really just assume that they are there and on screen. So we don't need to redraw these every loop. Okay, the actual numbers which go after these, obviously we will have to redraw those, but not the actual boilerplate code itself. We're then setting up a number of bits of our variables. So we are setting our bat y position. So really what we're doing here is we've got a number of constants defined. So if you remember when we went through our setup function, we did log down what size of screen we were working with. So we're getting it to automatically adjust the layout of our screen depending on the actual screen size that we find ourselves on. So that's all this doing here. It's saying that the Y position of the bat, so where the bat is vertically on the screen, which is going to be down near the bottom of the screen, we're basically saying we're going to use the screen height. We're then going to take off the bat height and the little 30 pixel margin. So that will put the top of the bat 30 pixels above the bottom of the screen. We've then got a number of other global things like our lives left, our score, and which level we're on. And then I have three little functions here which allow us to add the actual numbers in the correct positions after these blocks of text. And again, by pulling them out into their own little separate functions, it means that when we need to update those values, we have that code already written. So again, the code for putting the lives number on the screen is written once, and we can use that from various positions then. So once we get that information on the screen, then we eventually will call this function called initGameBoard, which is defined down here, and we'll come back to that in a bit because that is going to involve setting up our actual bricks and so on. But for this first bit, now that we've gone through the sort of initialization function, we're going to look at how we can get the bat moving, because that's the very first thing which we need to do in our game. So if we come back down to our loop function and into our state which handles the game playing, you can see at the moment I've commented out the actual code here. So remember what we said, where we're using our state machine. So when we're in state number 2, this block of code will be running each time that we come through our loop function. And that simply creates, in effect, one frame of the game. So if we comment out our move bat function, what that does then, if we have a look up for our move bat function, and that is up here. Okay, so we have our move bat function, and really what we're doing is we're going to be using the touch screen to control the X coordinate of the bat. So the bat is at a fixed Y position, and we saw that being set in the initialization code. But our X position then, so really when we call the function move bat, again we're going to really test, has the screen been touched? If it hasn't been touched, we're going to quickly get out of this so we can carry on doing the rest of the code. But if we have got a screen touch, which is that this if ts.touched, then we're grabbing hold of the touch panel coordinates. We're then converting that into screen pixel coordinates, and we're then using that X coordinate to set the mid position of the bat. So this line here is really just saying, of course, we have to signify the top left corner of the bat. So our X position is going to be the touch point minus half of the bat width. We're then just doing a bit of limit checking here. So if the bat has gone off either edge of the screen, we need to then just fix it at the edge of the screen. And then in this block down here, so this bit here, we are continuing this idea where we want to minimize the number of elements that we're redrawing on each game frame. Again, to make sure that we have enough time then to actually do all of the animation and so on. So if the bat hasn't actually moved by very much, we're basically saying don't bother redrawing it. We are tracking where the bat is. Okay, so we have to make sure that we do monitor all the movements on that. But what we're really saying is if it hasn't moved by more than 4 pixels, then really the user isn't really going to notice that. So let's not bother redrawing it. And that just saves us just a little bit of time. Because again, the slowest part of this code is when we have to communicate various items being drawn or removed from the screen. So let's have a look and see if that actually works. And so this is our move bat function, and let's upload that into Arduino and see if that actually does anything. So that's going up into our Arduino, and there we have it. Okay, so we're now in our screen calibration function. Let's just calibrate the screen, and there we're in our start game state where we have the button. We click on that. And we now have our sort of boilerplate text now in place, where we have our score, and again the numbers after it then are being driven by those three little display functions. And we should now, if we touch on the panel here, we should then have a touch event, and then our bat should now be attached to our pointer. Okay, and there we have it. And we can see if I move it here, and if I just make very slight movements, you can see that the bat doesn't move until we've actually moved it a certain number of pixels away. So that just means that, again, we're saving a bit of time there on not redrawing the bat every single loop. Okay, so that's the bat in place now. So the next code we need to get up and running is the ball. So really that's going to be a little circle which is going to move around the screen. So let's have a look at how that is brought into the code. Now, as usual, I've been working through a number of the variables. So we've defined a number of variables at the top of our code here. And these again are going to be global variables just to make it easier for us to use them throughout our code. And you can see here that we have then a number of variables which are to do with the position of our ball. Now we're actually going to use those as not as integer variables, we're actually going to do them as floating point variables. So you can see here I am defining them with a decimal point at the end of them. And we'll see why that is in a second. But if we go down to our game loop then, so somewhere down near the bottom here, right? So we know that we're in game state 2, where we are playing. So I've uncommented a couple of bits of our code. So we now have a move ball function. And I've also uncommented the check hit bat function, which actually means that's the bit that actually checks, obviously, if it hits the bat, so we'll let it bounce back up again. But let's have a look at our move ball function then. So if we come up here and we have our move bat function, and up here somewhere we will have our move ball function. So move ball function. So the move ball function then, so we have these floating point variables which dictate its x and y coordinate values. And by using floating point variables, that gives us much finer control over both our position and our velocities. If we just simply use integer variables, then obviously the smallest measurement unit that we can use is a single pixel. And if we start talking then about velocities, so how many pixels per loop it's moving in the x and y directions, we can only go integer values, so 1, 2 and 3. By going to floating point values then, we can obviously have much finer positioning information, and our velocities as well, we can have it moving half a pixel. And the idea here is that when we try and then plot that on our LCD screen, we will simply just round our floating point values to the nearest integer value. So although we are tracking and moving in very fine floating point variables, the actual positioning on the screen will still be fixed to its normal rigid individual pixel values. But that just gives us extra control. So we're modeling our movement at a fine control level, but of course we are displaying it at the integer value pixels. And again, that's a technique you'll need to use throughout your game coding, where you need to have your models running at the correct level of accuracy to give you the correct motions and responsiveness that you need for your game. And then, of course, you can simply convert those really accurate values to less accurate values that are needed in your actual display of what's happening in your game. So that's just a general sort of idea there. So basically here is then that we have an x velocity and a y velocity for our ball, and that just simply tells us how many pixels it will move per game loop in the x and y directions. So we simply then, once we come into our move ball function, we simply then update our x and y coordinates. We're using here a new x. So in effect what we're doing is we're saying the current position of the ball is given by the values x pos and y pos. We're then working out where the new position of the ball is going to be in these variables new x and new y. So at this point after this, so we will then obviously then limit check our new x and new y values. But once we get down to this point here, we now have X pause and Y pause, which tell us where the ball was the last time we drew it, and then new X and new Y, which is telling us where we now need to draw the ball. And we need that to be able to do this overdrawing technique. So all we're simply doing then is we're saying we have a function here called clear old ball position, and that simply draws a black circle over the top of the ball's previous position. We're then drawing in this line here, we're then drawing the new ball in using the new X and new Y position, so that will then have moved the ball. And then we're saying, okay, our last X position and our last Y position are going to be a record of where we've currently drawing it. And we update then our X position and our Y position. So we now have the idea where we are both keeping a track of the last position we drew the ball, and then working out the new position where we're drawing the ball, and using that then to do this overdrawing technique. There are other bits then what we've just uncommented. So we do have that check. So in the move bat, then we have a check hit bat function. So that is really just looking at the ball. So we have here, the ball is coming down, and we know that it is in a position of Y pause and X pause. And I'm using this check collision function here, and that is what's known as a bounding box collision detection. So we're simply saying here we have a bat, which is a rectangular object. We have a ball, which is in effect we can put it inside a square. So so all we're doing here is we're making a square, which is what's known as a bounding box for that circle. And then we're just working out this check collision function will come back telling us whether those two rectangular areas are overlapping. And again, I've done a whole video on bounding box collision detection, and I'll put a little link up in the top corner there. You can have a look at that. But basically, it's looking at the various edges of each of these boxes, and there's a certain set of conditions that we can check for, and that will tell us if those two boxes have hit each other or not. So really then saying is, if we are getting a hit, then we are going to alter the velocities of the ball to take account of that. And so we're really saying here then, so if we have a hit, then we are on the bat. So remember, this is checking for the bat. So we know that if we hit the bat, we will always bounce back up again. But what we're also doing here is we are gradually, for each time we hit the bat, we are gradually increasing its velocity. So as we play the game, the ball will actually get faster and faster and faster, up to this maximum velocity of 5 pixels per loop. And you can see there, so that's us in increasing the Y velocity and limit checking it to 5, and that's us then reversing the Y velocity. So if we hit the bat, we simply just reverse the Y velocity, and that will send the ball back up again. We're also, on our bat, we're not just having our bat be almost like a flat surface. We're going to model it as not so much a curved surface, but a non-flat surface. So if the ball hits one end of our bat, it will bounce off at a different direction to when it hits the center of the bat. So basically, if we hit the center of the bat, then the ball should do a sort of a normal reflection where we don't change the speed it's traveling left and right. Whereas if we hit the bat away from the center, then the further we are from the center of the bat, then the more we sort of model, in effect, a curved bat, so it will deflect at a different angle. And basically then, so if our ball is traveling from left to right and it hits the bat on its left hand edge, then it's almost like it will be sort of hitting a self-reflecting angle, so when it bounces off the bat, its angle will be less. Whereas if it was to hit the right hand edge of the bat, so in other words the sort of curve that's curving away from its motion, then obviously it will go at a shallower angle to the horizontal. And again, best we is when we run this, I'll show you that working. But in effect, what this is doing is it's modeling in effect a curved bat surface, so we get our different angles. And again, this is where we need to have our velocities and positions modeled as floating point values, so that we can get a much finer tuning of these angles. And then the last bit there is we make sure that the ball is not hitting the bat. So all we do here is once we have detected the ball hitting the bat, we want to then make sure it is now clear of the bat. So otherwise what would happen is that once we come through this function once, we would detect a hit and alter the direction of the ball. If the ball hadn't moved off the bat by the next time we came round again, then of course we'd have a second hit. So we simply just say, once the ball has hit the bat, we then place the ball above the bat, which is what's happening here, and then the ball will then no longer be logged against the bat and will travel on its merry way back up the screen. So that's really what we've brought into play at the moment then. And obviously there are other sort of various limit checking on the ball itself. But let's have a look at that working, and we should be able to then see the ball bouncing around the screen, and we'll then be able to check, and you'll see this rounded bounce effect taking place as well. So that's going up now to the Arduino. Give that a chance to come through. And that's initializing our screen then. And so we start off with our calibration function. So let's just calibrate that and then go into our play state. And we now have our ball coming down and again bouncing off our bat. So our bat now controlled by our touch screen and our ball then under our software control. And you can see now that we are modeling this idea of the curved surface on our bat. So if I'm able to get that to hit just one of the edges there, you can see that in the center our ball really reflects as if it is a flat surface, but then if I hit it at one of the edges, you can see we get that curved effect, and if I hit that edge again, it curves off to that side as well. So that gives us now our bat and our ball being modeled, and we have that again, that idea of that curved surface. So the last thing we'll need to look at then is getting some blocks on the screen. So the blocks in our game, we're going to model those in a slightly different way. So far all of the code we've been written has been using just individual little functions, and this is our procedural based coding, and that is perfectly fine. And you can see here that we are breaking up all the little blocks of our code into nice neat little functions, and each of these functions should be quite small and just handle a particular part of our code. So you can see here our hit bat function just handles that hitting the bat. So it's a nice succinct bit of code, and we simply then piece together lots of these little blocks of code to make up our actual function, but our actual program, sorry. But if we have a look then at how we're going to model our blocks, so in our init game function, which is just here, we've seen that we come through and we eventually create the sort of the boilerplate layout for our game, and then we have this init game board, and this first bit of it then is just setting up some various parameters, including our ball information. But we then come down to this block here, which I've just commented out. So let's uncomment that, and this then is a set of for loops. So there's one loop inside another. So we have rows and columns, and these are going to produce our blocks. And really what's happening then is we're saying here that we have 5 rows of 16 columns. And once we go through there, we're simply saying, so our first 2 rows are going to be blue blocks, and they're worth 50 points. Magenta blocks, 30 points, and our last 2 rows that are going to be yellow blocks worth 10 points. And again, that's going from the, when this is drawn out, it'll go from the top of the screen down to the bottom of the screen. And we're then, for each of those blocks, so each of these times through this loop, we're then going to create an object. And we're using this idea of a block object which I've created. And we'll have a look at that in a second. But really what we're doing is we're creating a two-dimensional array. And again, this is defined up here somewhere. We'll see that in a second, as one of the global variables. But that then is, in effect, an array of arrays, which gives us this two-dimensional. So we can then access those using a row and a column coordinates. So inside each of those elements in that two-dimensional array, we are generating a new block object, and we're giving it its information. So we're telling it, in effect, its X and Y pixel coordinates. So we're basically saying that each block is going to be 20 pixels wide. So we're going to have it, so its column position times 20 will give it its X coordinate. The rows then are going to be 10 pixels high, and we have an offset then of 30. So that's just really just making sure that in effect, those two little equations there will tell us that for a block at column and row positions, this is the pixel coordinates of its top left corner. So we're then setting its actual size. So we're using 19 by 9, which is just one less than this. And that will just then give us, instead of having solid blocks of color, this will mean that we have a 1 pixel gap between each of the blocks. So we can actually see the individual blocks then. We're then sending in a color value. So you can see here the color of the block is given by one of these coming out of our switch statement, and then the score, or in effect the value for whenever we hit that block, is again coming in here. So let's have a look at this block object, which is defined somewhere up here a bit further. So you can see here, this is where we're defining our two-dimensional array. So we're creating a variable called block, which is going to be, so each element in this variable is going to be one of our block objects, and then we're creating that as a two-dimensional array with 5 rows and 16 columns. But if we have to then look at the actual block itself, so this is where we are defining our C++ class. So again, we're saying here class block. Then we're defining its public properties. So we have an X and a Y, and those are going to be the top left corner coordinates of it. A width and a height, which of course is width and height, color and score. And then a final one here, which is going to be a Boolean value. So these are the attributes or the class members of our object. Is active is really going to tell us whether this particular block has been hit or not. In other words, is it actively being shown on the screen, or should it not be drawn? So when we create classes inside our C++, we have to generate a number of methods for that, and one is the constructor method. And to allow us to do this sort of statement, where we are creating an array which is going to hold eventually block objects or instances of our block class, we need to have a default constructor, because that sort of will be something which this needs to do. So we're not yet calling its main constructor, so that's the constructor that we're going to call when we instantiate an actual block object, but we need a default constructor so that our code understands how to reference our block classes. Okay, so this is needed to allow us to define arrays based upon this object. Okay. We then have the actual constructor value itself, and we've seen then that if we come down to our init game board, we can see here that this is where we are instantiating an actual object. So that will call its constructor, and for that constructor then we need to pass in the information that defines this block, and we've already seen how that's generated. So that, if we come back up then to our class definition, you can see here that really we are catching these setup parameters for this particular block, and then really just storing those into the class attributes. So again, so these X and Y values are actually referencing these class attributes which we defined up here. So we're really saying then, so the incoming X position, which is going to be the left and right position of the top left corner, we're simply storing that in the X attribute. Then the incoming Y pos is stored in this Y value, width, height, color, and score. When we first instantiate a block, it hasn't yet been hit, so we're saying that this is an active block. And then we're calling one of the block class's methods, which is drawBlock. So again, the idea here is that when we create a class, this is going to model a block on the screen, and it should also then have built into it the code that handles that particular object. So for a block, it needs to know how to draw itself. So here we have our draw method. So when we first instantiate the block, it draws itself on the screen, and that's just drawing a rectangle in the correct place, at the correct size, in the correct color. And again, all those values have been sent in this constructor itself. Our block then needs to be able to tell if it has been hit or not. So really it has this method then is hit, and inside that we will send in effect a rectangle which will be which will actually be generated from the ball itself. So we have a top left corner of a rectangle and then a width and a height of our rectangle. It's then going to use this function called check collision, which we've written around here. And again, I'll have a look at that in a second. And that really then just brings in the ball rectangle. So again, that ball rectangle then is being sent in through these parameters. So we're using that as one of the rectangles in our collision detection. The second rectangle in our collision detection is of course the block itself. So we're using the X and Y coordinates, which is the top left corner, the width and the height. And then this function back will then send us back either a true, the ball has hit this block, or a false, that the ball has not hit this block. And we're simply then returning those back out. And this method will be used in our ball and block collision detection elsewhere to decide when the ball has hit a block. When the block is hit, then we will ask the block to remove itself from the screen. So this is where this function in here again. So we're really delegating all of the code which relates to the block. We're actually building that and embedding it inside our class. So this is the idea of encapsulation, where this block now we can in effect give it commands. So we can ask the block to draw itself, we can ask the block to remove itself from the screen, and we can ask the block, are you being hit by this ball coming in? So that's a sort of, again, a different technique of building your code. And again, for me, I'm a fan of object-oriented coding, because it lets me say, okay, here is a particular object which is part of my code, and I can then encapsulate all of the data and the code that handles and models that object inside this class. And then I can create multiple instances of my class, so I can instantly have however many blocks, so 5 times 16 blocks, all handled on the screen, and I can individually address them and ask them questions and make them do things. So if we come back down to our init gameboard function, so this init gameboard function then, at the moment then, it's going to go through, it's going to run through each row and column and put a block in each of those rows and columns. And as we've already seen then, part of the constructor for generating or instantiating a block object is for the block to actually draw itself on the screen. So we've got that code now uncommented, which means that if we now come back down to our loop function down the bottom here, so once we come through here and we init our game, At that point, we should now get a set of blocks appearing on the screen. Okay, we haven't yet included the code here which checks for us hitting a block. So you can see here we have a little function call which will eventually get there. But we should be able to upload this and actually have our grid appearing on the screen. So let's put that up into the Arduino and get that uploading in there. And there's our screen coming through. So again, we go through our calibration function into that, and there we have our blocks appearing on the screen. Now, as I said again, the blocks are simply drawn onto the screen once those block objects are instantiated. So as our ball is moving around, it's not yet detecting when it's hitting blocks, so it's just being animated, moving all the way through them up to the top of the screen. And you can see there that as the ball path is being drawn, and again it's being drawn in terms of rubbing out the old position by simply putting on a black circle and then drawing the new position, you can see that we are getting then these tracks being left through our blocks. But at least all of our blocks are appearing on the screen in the correct position, in the correct colours, and those are being put on there using these objects, so instantiating objects of that block class, which then understand where they are on the screen, how to draw themselves, eventually how to detect collisions with the ball, and then how to remove themselves. So let's have a look at how we can get that block of code then working and get our game heading towards its end state. So let's look at getting the ball hitting these blocks. So if we uncomment this next line, you can see we already have written a function there called check hit block. And of course that's going to check if the ball is hitting a block. So let's come up here and see what that does. So here we have it. This function basically then needs to loop through every single element in our blocks array. So remember we have this array called blocks, which is a two-dimensional array with rows and columns. And each of the elements is an instance of one of our block objects. So here again we have our row loop with an inner column loop, and that will of course get us through every single element. So we're checking each individual block then. So first of all, is that block active? So remember we added an attribute into our class which told us whether that block had already been hit or not. So we're only wanting to check blocks which have not been hit, so blocks which are active. And then remember we added a method to our block class, isHit, where if we give it a rectangle, it will check to see if that rectangle is overlapping with the actual block itself. And that will then tell us that this whatever rectangle we pass in, and you can see here we're passing in the actual ball itself. Remember we're converting the circle of a ball, we're putting it inside what's known as a bounding box. We're passing that into our isHit method, and then we will do a collision detection between the rectangle of the block and a rectangle or the bounding box of the ball. So if it's active and it's being hit by the ball, then we simply have to, again, we're calling a method inside our block class, where we can get it to remove itself from the screen. We're then incrementing our score. So remember, each block has built into its class what its value is when it's hit. So we're increasing our player score by the score value of this particular block. We're then redrawing our score up in our top boilerplate area, and again by bringing that out to its own separate little function, we simply need to call that, and that will automatically handle deleting the old score and adding in the new score. And then we're simply reversing the y velocity. So in other words, if we had been traveling up, this will make it travel down. But it also means that if our ball has got above the blocks and is traveling down to hit the blocks, it will then bounce back up towards the top of the screen again. So we just simply need to reverse the y velocity. And we then want to actually leave this function. So the next line here is that, so if we have detected a hit on a block, we actually want to return from this function and not bother checking any other blocks. So we're just checking for the first block that we notice the ball is hitting. And really that then saves us from because if you think about it, if the ball could be hitting right between two blocks, and at that point we will get the situation where it will reverse its direction for the first block and then reverse its direction for the second block. So really we just want to, as soon as we have one block being hit, at that point the ball will bounce, and then we need to get out of this loop. If it then continues to hit a different block, it will then be detected on the next loop round on this, but we're just detecting one collision per loop. And then we return back from that function. So you can see here that that is quite a simple function. Again, all of the complexity of how to work out whether a block is on the screen, whether it's being hit by the ball, how to get it off the screen, what its score was, all of that complexity has been encapsulated inside our block object. And that's one of the real reasons why I like object-oriented coding, because we can do that. Once I've worked out how a block calculates if it's been hit or not, we can bury that inside the class, and then we can just simply ask that class or that object, are you being hit? And our code out here, it almost makes English sense. Okay, so we can simplify our code out here to make these sort of global or more English-like method calls and method checks, which just really makes, once we come back in to look at this code, it makes it just more easy for us to understand what's going on. And if we have to delve into how it actually does remove itself from the screen, we have that nicely encapsulated in a nice little method inside our class. So again, if you're not familiar with object-oriented coding, I do advise it is well worth getting yourself familiar with it, because it does greatly help improve the speed at which you can code and reduces the complexity in effect. But anyway, so that now should give us the idea where we can now hit the blocks and have them removed from the screen. So let's again try that out and see if it works. So let's put that up to the Arduino. That's going in, and we should get into our calibration function now. So let's calibrate the screen, click to play, and we should now be able to hit the blocks. And there we can see we now have our actual game taking place. Okay, so we can see that that's now working, and really all that's left now is to do some of the sort of housekeeping on our game actually getting towards an end state. So we need to now look at what happens when we've hit all the blocks. We need to work out what happens if we miss the ball, and really it's just a bit of tidying up now, but the main block of the code is now written. So let's come back down to our main game loop, which is in state 2 down here. So we've got the ball, bat moving, checking hits on the bat and the blocks. So let's have a look at what happens when we miss the ball then. So this is the next block of code I have in this listing. So if I do that, and let's just leave this last bit down here still commented out. So we need to check if we have lost a ball. So that's really just if the ball has now gone off the bottom of the screen. So if I have a look at this function check ball lost, so if we come up here, so that should be around here somewhere, check ball lost. So again, that's really quite a simple function. So if the Y position of the ball is greater than the height of the screen plus the ball size, so it's actually gone right off the bottom of the screen, then our ball we've missed that ball. So remember, our bat is a certain number of pixels above the bottom of the screen, but we don't want the ball to signal it's lost just as soon as it goes below the bat. We actually want it to physically disappear off the bottom of the screen to make it look like the ball really has disappeared away from our play area. So that's all check ball lost does, a very simple function. But we come back down to our game loop then. So we're saying, so if the ball has gone off the bottom of the screen, then we've lost one of our lives, and we then update the display on the screen. So remember, we're only updating these numbers when we need to, again, to reduce that number of draws out to the TFT. we're saying then if we still have some lives left, so if we've got greater than 0 lives left, then we're going to create this function called new ball, and that's going to then restart the ball for us. So if we've lost all of our lives, then we go into our end game state, which is state number 3, which is down the bottom here. And again, we've already looked at that, and that just simply puts up your final score, and then effectively then goes back up to the start screen where it asks you to click to play. But let's have a look at this idea of new ball. So if we come up here and look at new ball, which should be not too far from there, right? So again, when we create a new ball, this is very much the same as when we initialize the game. So we put the ball back to its starting position, which is over at the left-hand side of the screen and below the blocks. We reset its velocity, so it's traveling at 45 degrees, and then we call the move ball function to actually put it on the screen. We then have a delay of 1000. So again, that gives the player a chance to notice that the ball has respawned and get back in position to get it. If we didn't have a delay there, if you had just missed the ball, it gets a little bit difficult to then get back into the game and get right back in to catch the next ball. So that just makes it a little bit more playable. But you can see it's very simple, because we know that the positioning of the ball and the drawing of the ball is handled by this function. Our creating a new ball just simply needs to reset the values that model that ball, and then our functions will take care of that. So let's have a look and see if that works. So we've now got that coming up into our Arduino, and there we're into our calibration screen. So we calibrate that, click to play. We can now play our game. If we now miss the ball, that comes up, it resets, pauses, and now we have our next ball. And again, we've lost one of our lives. So again, if we lose our life, lose a life, and we're now into our end game screen where we see our score, and we can of course click to play again. Okay, so that's all up and running. So pretty much the last thing we need to look at then is what happens when we've hit all of the blocks. So if we come down to our main game loop again, so you can see again, if I just uncomment this last little block, you can see again we have another function which is going to do this check for us. And again, by breaking all of your code out into functions, it means that your main game loop, you can see here, again, it makes much more sense as you read through it. So if all blocks have been hit, then we go to game state 4, which is going to be setting up the new blocks. And you can see here that that's putting in a delay. It is then leveling us up. And again, the level is being drawn on the screen again using another one of these little helper functions. The level itself then, we've already seen that at certain bits to do with the game speed and so on, the ball speed and so on, that level is used in there. And then we have our init game board, which again is our little function which we broke out, which resets the ball and resets the blocks. So we've already been through that. But let's then have a look at this new function and check all blocks hit. So if we come up here to have a look at that one, so check all blocks hit. And really all we're doing is we're counting how many of our blocks are active. Well, actually, we're just really looking to see if any of them are active. And as soon as we find an active one, we will return back false. We have here our loop, which is going through our rows, and then each column in each row, checking each of the elements in our blocks array and asking it if it is active. If we find an active one, then we obviously haven't hit all the blocks, so we can return back false from this function. If we get to the very end of our double layer loop, then that means that we haven't found any active ones, so we can return back the value true, which says that all the blocks have been hit. And at that point, as we've already said then, if it comes back with a true value, we know we've hit all the blocks, so we simply then generate our new game screen and off we go again. So again, let's see if that works. Well, actually, if I do it at the moment, we obviously have to hit all the blocks. So what we could do here is have a look at our init game board and just modify that for our testing purposes. So let's come up here and find our init game board function, which is near the top. So here we are. So init game board, and we go through, right? So we go through every single row, every single column. We make a block in that column, and we know that when we instantiate our block, it sets it to be active. So all I can do in here, so I could say, so if row is equal to, so if we're in row, let's say row 0, and column is row, so we'll put a block at the top in the middle. So we want to select that block, and we obviously want to select the inverse of that. So if I do, so if not that, okay, so this inside here, we want to select row 0, column 10. And what I'm going to do is I'm going to say, so if it's not row 0, column 10, then what I want to do is I want to say, so blocks row column dot is active equal to false. So setting its is active to false will indicate that this block has been hit. But of course, if it has been hit, we need to make sure that we take it off the screen. So we simply need to do our blocks row column, and then we will call its function, so remove, or its method, remove block. So that means then that once we come through here, we are filling up our blocks array with instances of our block class. So we need each of the elements in our array to be an actual block, otherwise our code will fail later on when it tries to access that block. But then we're saying that if it's not this single block that we're looking at, then we want to mark it as being hit and take it off the screen. So in effect, what should happen at the end of this function is that we should only have that single block on the screen, and that being the only block which the system thinks is actually still there. And that just makes it easy for us to test this final end point where we hit all the blocks. Otherwise, we've got to play the whole game all the way through every single time we want to test this function. So let's see if that works. So that's coming up to the Arduino. We're into our calibration screen. There we go. And we click play. And we now have a single block on the screen there. So hopefully if I can at some point manage to hit this. There we go. We can see the screen being, you can almost see the screen redrawing through those blocks. And we can of course then, we can see that our level is increasing on each of the screen clears. And obviously we are back then to playing our game. Okay. Well, that's the whole game complete now. So hopefully you've seen then, as we've gone through there, we're using our LCD screen and our TFT touch panel. So hopefully you can now see how we can start to use that for user input. And again, here using it as a game controller. We've got the LCD screen, and hopefully you've seen some of the techniques there where we're simply trying to reduce the number of times we have to send information to that screen. Again, going across this serial SPI interface, especially with just the single data connection, that is really the slow part of this whole system. So the fewer times we have to draw information on the screen, and the smaller those pieces of screen that we're drawing are, then the faster we can get the frame rate going to give us a smoother game. And again here, the idea is that we are only drawing, basically we're only drawing the bat and the ball. So the bat's only being drawn if we move it more than about 4 pixels. The ball is the only really thing that's being drawn every single frame. All of the blocks are drawn once and then just simply removed whenever we hit them. So that gives us then our frame rate. So hopefully that gives you some ideas as to what you can then go on and do with your own coding, and hopefully have some fun with that. So I hope you've enjoyed this tutorial. Please make sure you visit the course page, all the links in the description below, to get the code and more information about this. Do make sure you subscribe to the channel and like the video, and hopefully I will see you in another tutorial. So bye for now. Don't forget to visit the course pages for this project. There you'll be able to download the code for this lesson and get lots of extra hints and tips. You'll also get access to all my other programming, electronics and gaming projects. All the links are in the description below. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.